Hello, everybody. My name is Chunhua Shen. I'm going to present some work we did in the past 2 years in the area of instance level recognition, in particular instance segmentation. So mainly we developed a few methods which significantly simplify the pipeline for instance segmentation and a few other instance level recognition tasks. The work I'm going to present here are mainly done by my former PhD students. There are quite a few fundamental perception tasks in computer vision, including, for example, depth estimation, key point detection, semantic segmentation, instance segmentation, object detection. And for those tasks, mainly there are two categories. The first category, for example, depth estimation and semantic segmentation. Those tasks can be solved using the standard fully convolutional network. Mainly, it's usually it's encoder decoder framework, right? So it's pixel wise supervision in the training and pixel wise prediction in inference. However, for the instance level tasks such as object detection and key point detection and also instance segmentation, typically those tasks cannot be solved by using the same fully convolutional encoder decoder framework, mainly because given an image, one needs to detect each instance first. Then for each instance, we just solve the like a key point detection or instance segmentation tasks. Therefore, in general, the instance level recognition tasks are the pipeline is more complex than this fully convolutional encoder decoder framework. And here, the main motivation of our work is, we try to largely simplify the pipeline for instance level recognition tasks, and hopefully we can develop a framework which is compatible to this fully convolutional encoder decoder approach to solve instance level tasks. Before I present the instance segmentation methods we developed, I'd like to give you a very brief introduction to the focus object detector. Focus stands for fully convolutional single stage object detection. This is the work we published in ICCV 2019. So the main idea of focus object detection is very simple, right? We try to remove this so-called ink box design in most of the single stage object detection framework, right? In this paper, basically we show that you can safely remove the ink boxes from object detector. At the same time, you can still achieve state of the art accuracy and inference speed. So here, this plot just show you the main idea. So it's very simple, right? So given image, we have this FPN, the feature pyramid network, to extract the features, and for each of the hierarchical the features, we attach a head to each level of the features, and for the head, basically we need to do two subtasks. One is of course the bounding box regression, and the second is the category categorization, the classification. And here we actually also introduce this so-called sentence. It's optional. We show that once you include this sentence measurement, which can improve the accuracy. So this is by far probably the simplest object detection framework, and it's fully convolutional. Because of its simplicity, now it's much simpler to like extend object detection to solve other relevant instance level recognition tasks, such as instance segmentation and key point prediction, for example. Here I just show you some of the visualization of the detection results. Just to demonstrate that the focus object detector works quite well. Okay, as I said, the main advantage of this focus object detector is, the by design the framework itself is much simpler, and it's very easy to extend to other tasks, right? As I just mentioned, and then now detection becomes a per pixel prediction task using the fully convolutional network. It's pretty much the same as those fully convolutional networks in semantic segmentation. And when we compare focus against those state-of-the-art object detection methods in terms of both the speed and accuracy, the focus object detector is among one of the best methods. Okay, so next I'm going to show you how we can extend focus to solve the more challenging instance segmentation methods. Right. So last year we published a CVPR paper. We call the method blind mask, and we ask ourselves a question: can a fully convolutional network compete with the mask-RCN framework, right? So I guess everybody knows that mask-RCN is still one of the state-of-the-art instance segmentation methods. It's a two-stage approach, right? So in the first stage, you detect each of the instance bounding boxes, and then for each bounding box, you need to predict the mask, and get the mask and the category label for each object in the image. Okay, just a few words about the instance segmentation. So instance segmentation really it's just the pixel level object detection. Right here, I just show you some examples from the Microsoft COCO dataset as well as the Cityscapes autonomous driving dataset. Right, so compared with semantic segmentation, besides we need to predict the category label for each pixel, we also need to predict the if a pixel belongs to one particular instance or not, right? And compared with the bounding box object detection, so we instead of to predict the bounding box, we now need to predict the instance mask, which is of course more challenging. But at the same time, the instance segmentation results can provide much more accurate information compared against the bounding box prediction. So this is the the popular mask-RCN framework. As I just said, basically, in the first stage, you have this so-called faster RCN object detection to get each bounding box, and then for each bounding box, we extract the features. Actually, the mask-RCN paper developed this feature alignment method called ROI align to extract the features for each box, and then for each bounding box we have the mask prediction as well as the category classification tasks, right? And then you get the the per pixel instance segmentation results. The main disadvantage of mask-RCN is the computation complexity of the mask prediction head is linear in the number of instances given an image. That's the reason why the output resolution of the mask prediction head cannot be of very high dimension because of the computation complexity. The most relevant work in the literature to blend mask is this so-called UACT, which was published in RCCV 2019. So the idea of UACT is a single-stage instance segmentation method. The idea of UACT is, you have this object detection branch which detects the detects the bounding box for each instance. At the same time, the detection branch learn a linear mask coefficient for each channel of the features at another feature branch, and then you use the bounding box to crop the features and linearly combine all of these cropped features, sum them up to get the instance mask prediction. Our blend mask method can be viewed as an extension of the focus object detection, also an extension of the UACT method. Right? Instead of learn a linear coefficient for each linear mask coefficient for each channel, we actually learn a attention map. Right? So because of this much more powerful representation embedded in the attention map compared with the linear scalar coefficient in UACT, we can use like a very small number of feature maps. For example, we can only use just 4 feature maps, and the UACT actually use 32 feature maps. Compared against the mask RCA method, our method is even faster and achieve more accurate mask prediction. So here I just use the simple pipeline of blend mask. Given image, we have this again the feature pyramid network. In the middle, this is basically the focus object detection module, and the detection module predicts the bounding boxes. Also, attention map for each channel of the here the bottom module is the feature maps, and then we linearly combine them to get the instance mask prediction. So we align them with attention to the same size, and then we here this plot shows the element-wise multiplication of the attention maps to each corresponding the features, the feature basis, and combine them to get the instance prediction. Okay, so the blend module here is actually closely related to other detect then segment methods, which also merge instance and local information. It can be considered as a generalization of this category of methods. For example, UACT can be considered as a special case of blend mask by setting the top level attention to a single vector instead of a tensor in our blend mask method. And the FCIS paper published by Microsoft Research Asia is a special case with hard-coded one-hot attention and nearest neighbor interpolation. When compared head-by-head, our blending mechanism actually shows better flexibility and higher accuracy with less number of parameters. This table shows some of the numerical results. Right? The message is the blend mask works better in terms of both speed and accuracy compared with some of the methods in the literature under the same training schedule. Here I show some of the visualization. As you can see, one of the main advantage of brand mask is, the segmentation results of, it's more, it preserves more detailed information, especially at the boundary. Mainly because, brand mask can successfully identify separated parts as an entire instance and preserve their high resolution details compared with UACT and mask RCN. And we can also easily extend brand mask to panoptic segmentation tasks. And here I just show you some of the numerical results on the Microsoft COCO dataset for panoptic segmentation. Okay, the second instance segmentation method I'm going to talk about is conditional convolutions for instance segmentation. This is a paper published in last year's ECCV. So the brand mask method I just presented, it's still based on object detection, right? Same as mask RCN and UACT. We still need to predict the bounding box for each instance first, and then actually at the same time, and then to predict the instance mask. So now we ask ourselves a question: can we actually eliminate the bounding box prediction from instance segmentation? Right? We don't want to predict the bounding box. Can we just directly predict the instance mask for instance segmentation? There are, with bounding box prediction, there are actually a few issues related to this axis alignment, the region of interest, right? For example, here in the left figure, if we want to segment like a pencil, because of the shape, a bounding box cannot really will represent the object instance, right? And for another example is the OCR, text detection and recognition. Bounding box in this case is not a good representation either, right? So if we can remove bounding box from instance segmentation, then we don't have to worry about the feature misalignment issues. Okay, so let's check the difference between instance segmentation and semantic segmentation. Here, I just show you, like the top row shows the semantic segmentation. In semantic segmentation, we only need to predict the category label. We don't have to distinguish one instance from all the other instances, right? But the bottom row shows the instance segmentation. We need to distinguish a person from all the other persons in the image. So that's the main difference, right? And if we just recall for the methods like mask RCN, UACT, and brand mask, the bounding box. What's the purpose of bounding box? Really, the main purpose is to distinguish different instances in the image, right? Because you just need to you detect the bounding box first, and then for each bounding box you predict the mask. Can we find another way to another mechanism to distinguish different instances of the same category, which might be the same category? And this is what we want to achieve in Context. Here I just show you the pipeline of Context. Right? If you compare this figure with focus detector or the brand mask instance segmentation framework, it's actually quite similar. Here, instead of using bounding box to encode the instance location information, we actually use the so-called dynamic convolution to encode, the location information, the instance specific information. The main idea is instead of to detect the bounding box here, we actually, the module in the dash box here, let's call it a controller, right? This controller actually takes a feature vector relevant to a particular instance in the image as input, and then the controller generates these conditional dynamic convolutions. And once we apply that convolutions to the feature map, here the bottom branch is feature map, and hopefully the convolved results will be the mask for that particular instance. So that's the main idea. And then let's see how this dynamic instance aware the convolution works, right? So here, just give you a illustration. Given an image, we have the backbone network to extract features, and then once we we generate a proposal feature vector for each instance, and then we input that feature vector to the controller, and then the controller generates instance aware convolutions, and then we apply the convolutions to the bottom module's feature map, and then ideally we want to have the instance mask as the output. So as you can imagine, if we have say 10 instances in the image, then we need to do this dynamic convolution 10 times for for each of the instances in the image. That's how it works. And here I just show you some of the visualization results. Again, our predicted masks are more detailed, especially at the boundary. So the main advantage of CONINST, we call it CONINST, is now we can just eliminate the bounding box prediction. Therefore, the ROI operations from the pipeline of instant segmentation, and now it becomes fully convolutional, entirely fully convolutional. And because of this, elimination of ROI, we can better deal with irregular shapes due to this elimination of feature misalignment, and we can output high resolution mask predictions. Right, compared with mask casting, the output resolution of our method is much higher, and it's fast in training and inference. Okay, so the third instance segmentation method I'm going to talk about is we call it SOLO. It stands for segmenting objects by locations. Again, this is a work published in last year's ECCV. So the key question we want to answer in this SOLO paper is, can we convert instance segmentation into a per pixel classification problem? Right? If we can do that, then we can solve instance segmentation basically exactly the same way as semantic segmentation, right? Because semantic segmentation is a per pixel classification problem. It's very simple, right? Okay, so again, let's check, the difference between, the fundamental difference between object instances given an image. If we look at this image of two zebras, right? These two zebras appear almost the same in terms of the appearance. And in this case, of course, we just distinguish these two zebra instances by the location, because they're in the different locations of the image, right? So basically, we, as a human, the human viewing system just distinguish this same category of instances by the instance location, and of course also the object shape, right? So if we can achieve that, then it is possible to solve instance segmentation by per pixel classification. Okay, so in order to use the formulate mechanism to exploit the location information, we quantize the locations, right? Same way as in the YOLO object detection, we just split the image into cells, and then we introduce the notion of instance category, right? If the center of an instance fall into one of these cells, we say this instance belong to this particular instance category, right? If we divide, in this case, we divide the image into 5 by 5, a grid of 5 by 5, then we have in total 25 instance categories, right? And if we can just classify each pixel into this so-called instance categories, then we have the mask. We can predict the instance mask. Then to predict the semantic category, it's very easy, right? It's the same way as semantic segmentation. Then if we can do that, then the problem is solved. By the way, in the recent paper, Pixel to Sequence, actually, the authors also quantize the locations. Well, basically the bounding box coordinates. All right, so then this is the the overall framework, as I just said, right? So given image, we have we goes the input image goes through the fully convolutional network, and the fully convolutional network have two branches. One is the semantic category branch, and the second branch is the mask prediction branch, and because of this this introduced the notion of instance category. Now we can predict the mask just by solving a per pixel classification, same way as semantic segmentation, right? And once we have these two pieces of information, we combine them, we get the instance segmentation results. And now in this case, instance segmentation can be solved by just two per pixel classification tasks. So it's very simple and it's fast to implement. Also, it's more straightforward to train and test. And compared against the mask RCN, as you can see, our solo method is much more simpler, right? It's a pure fully convolutional network. Here I have a video. This test video is just downloaded from YouTube, and the model is actually trained on Microsoft Cocoa dataset. The backbone is ResNet 101. As you can see, actually, it works quite well. Just speed up a little bit. And the second part of the video is autonomous driving street scene. And again, it works quite well. Remember, this model is trained on Microsoft Cocoa. It's not trained on Cityscapes or Kitty or this kind of autonomous driving datasets. Okay, so the key messages of this solo is we introduce this so-called location as category, right? We call it instance category. Um, the notion of instance category. This is a key idea. And, a few small designs like a feature pyramid network. Of course, everybody uses feature pyramid network for object detecting and relevant object instance level recognition tasks. And we show in the paper we also show that coordinate convolution and this dice loss also contributes to the final performance. The next piece of work I just want to very briefly mention is this we call it BoxInst. This is a paper published in this year's CVPR. So in this paper we show that we can train reasonably good instance segmentation model only using the box annotation without any pixel level annotation, and we can still achieve quite good accuracy. The idea is it's similar to the CIF, the graphical model. CIF graphical model. We have the unary term and we also have a pairwise term. I'm not going to get into the details because of the limited time. And as you can see on the Microsoft Cocoa dataset, our BoxInst works very well. It actually significantly outperforms the previous methods in this setting. And another piece of work I want to mention is this, we call it fully convolutional pose estimation. It's also published in this year's CVPR. It's similar to CONDINST, but we just adapt that framework to solve human pose estimation. And all of these methods I just mentioned are open sourced on GitHub. For anyone who is interested, you can download the code and just try. Thank you very much.